In this lecture, we want to continue looking at linked lists. In particular, we want to look at mechanisms for developing methods to manipulate linked lists that are correct and will work under all circumstances. Unordered lists first. The data is not stored in any particular order. There are many times when order doesn't matter, or if the list is to be used to build something else, such as a stack or a queue. If you are using a linked list to build a stack, of course you don't want an ordered linked list, because stack behavior requires that the first thing off of the list be the last thing into the list. Therefore, the idea of it being ordered in some kind of sequential order makes no sense. Unordered lists must have a head pointer. There has to be a way into the list, and may have a tail pointer if there's a requirement for insertion. So if you want to build a queue using a linked list, you almost certainly must have a head and a tail pointer. However, remember that removal from the tail end using a tail pointer is not possible. That is, we cannot remove from the end of the list using the tail pointer. We must use the head pointer to remove from the tail of the list. Thus, if we must remove from the end of the list, then we have to start at the head and traverse the entire list until we get to the end, and then use a trailing pointer to remove that final node. For big O of 1 behavior, since order doesn't matter, then insertion should always happen either at the front or the rear of the list. But if deletion can occur either place, then always prefer to remove from the front, because a tail pointer does not support deletion. I want to take a look here. Notice that with a linked list, the links only go one way. That is, we go from A to B, from B to C, from C to D. If we have this tail pointer here, D, how could we possibly remove D from the list? What we would need to happen to remove D from the list, we would need to make the following changes. This node, C, would have to have its next node set to null. And then the tail pointer would have to be C. How can we get to this state using only the tail pointer? Because there's no way we can get from D to C so that we can change this node. It's not possible. The links only go one way. Now, sometimes students think that perhaps we could solve this problem by having another pointer here and maybe call this before tail. And this would have C in it, and then we would have a reference to C. And having this reference to C, we could easily remove the terminal node by using the before tail pointer. Well, that's true, but it would only work one time. Imagine then that we remove D, and now we need to remove C. But we don't have a pointer to B. Therefore, this kind of strategy of having two tail pointers doesn't really work at all. It will work one time, but not after that. To be able to delete from the tail end of the list using a tail pointer requires a doubly linked list, but that adds extra overhead that has no real benefit. So I hope you can see we cannot delete using the tail, but we can delete from the head. Here I can say head gets head.next. This will put a B in this node. Head gets head.next, puts a B here. And now the A is effectively severed from the list with no problems. And now the list starts at B. This is garbage collected because nothing points to it anymore. So we can easily insert or remove from the head, but we can only insert at the tail. So imagine that I need to do an insertion at the tail here. I can make a new node, let's call it E. And put some data in it, doesn't matter what it is, let's call it a 5. This is initialized to null. All right, I want to insert at the tail. How can I do this? I can easily say tail D dot next gets new node. Tail dot next gets new node. D dot next gets this new node E. And then I can say tail gets new node. And now we go from B to C to D to E. And E is the final node, and it has the tail pointer indicating it. So we can easily insert either at the head or the tail. However, we can only remove from the head. Or if we must remove the final node, we have to start at the head node to traverse the list because we need a trailing pointer. We need a trailing pointer in order to remove the last node because we need a pointer to the next to the last node in order to set its reference to null. With ordered lists, the data is stored in sorted order as defined by the comparable interface. That is, the data items in each node are ranked or ordered based on the comparable interface. Ordered lists are appropriate when order matters, and there are some applications where order is essential. Ordered lists must have a head pointer because you need a way into the list, and the head pointer is that way in. But a tail pointer is basically useless because you cannot insert into the end position. Recall that with the tail pointer, you can insert but not remove. But you can't insert into an ordered list at the end because that might break the ordering of the list. And so when you do an insertion, you have to do it in order. Thus, you cannot use a tail pointer to insert. You cannot use a tail pointer to delete. Therefore, it has very limited usefulness. The only real functionality that would be of any use at all would be to get max or get last. However, again, this is something that's not terribly useful. And in general, keeping that tail pointer correct, adding code necessary for insert and delete operations to maintain that tail pointer is probably more trouble than it's worth. Thus, insert first, insert last, remove first, remove last operations make no sense in the context of an ordered list. So you're going to have precisely two methods. Insert, meaning insert in its proper position such that the list is ordered, and delete, find and remove an arbitrary object from the list. Linked lists are by their very nature prone to programming errors. Problems occur when you leave your linked list in an inconsistent state. This may happen where the list is split into two separate lists. We may have nodes with circular references, or the list can be truncated or contain invalid references. The null termination may be missing or in the wrong place. These types of errors are fairly common, and when they do occur, they are difficult to track down and find. So I want to reload my basic linked list here. So let's assume this is our basic linked list here, and we're going to put some data in it. 5, 7, 9. This one just happens to be in order, but this discussion is appropriate for all linked lists, ordered or unordered. There are certain things that happen fairly often. Suppose there is a programming error, and the programmer ends up doing this. We go from A to B to C to A. Now we have a circular linked list that has no end because it is the null at the end of the list that terminates the list, And so this causes infinite loops. This causes behavior where you're trying to search for something or delete something, and you get into this cycle that never ends. This is a common error. Another error that happens is when the student does something like this. We go from A to B to C, and from C to C. Amazingly easy to do this. So when you say we want to go to the next node from this C, we go to C. So you end up with this loop on a single node and go nowhere. Another fairly common problem, an unfortunate one, is when the list ends up getting severed. So we have a situation that looks like this. In this case, we now have two separate linked lists. So the scenario that we often see is the student will insert at the tail of the list and remove from the head of the list. So let us say that a student inserts a new node E at the tail end of the list, increments the current size. So this becomes E. So the student has actually inserted a new node into the tail of the list and incremented the current size, but there's no way ever to get to the E. So you start at the head and you try to remove E, but you get to this null value, and that indicates that the list is at its end, and there's no way to get from B to C. In fact, there's no way to get to C at all, and so since nothing points to C anymore, it ends up getting garbage collected. And then once you've inserted E at the tail, nothing points to D anymore, so it gets garbage collected. So you end up with a linked list here and a linked list here that has only a single node in it. So as you can imagine, this causes all kinds of problems when you need to debug and figure out what's going wrong. Erroneous behavior often occurs in a different place than where you see the error occurring. So in the cases that we talked about, if an insertion method is wrong and it leaves the linked list in an inconsistent state, this probably won't be revealed until you perform a search or do a delete operation. Very often, these errors occur because what is missing? An overlooked case. That is, there's a base case for an insertion, and then we need to consider the outliers. For instance, if you have an unordered list with a head and a tail, if you perform an operation and neglect to, say, update the tail pointer when you needed to do that, that will leave the list in an inconsistent state. So errors of this type either result in a null pointer exception or an infinite loop. So the program will either hang or it will crash. Try-catch blocks are often helpful in diagnosing problems caused by null pointer exceptions. For the infinite loop type of problem, the best approach is to put print methods into all of the loops until you figure out which loop is not terminating. Then you can find the problem. In this case, I have given you an example of a try-catch block that can be very helpful in finding problems. So here we have a linked list checker. This is a tester or a driver program that a student might write to test his linked list. Notice how I've constructed this. Students often get these driver or test programs wrong. The static causes a problem. So what I have here is public static void main at the bottom, and now I say new linked list checker. And inside the constructor for the linked list checker, I start or launch the series of tests we want to perform. So in public linked list checker, the constructor, I have a try-catch block. And so I create the linked list, and then I call the run tests method, which is not shown on this slide. Notice the try-catch block. The catch block, if an exception gets thrown, then the code in the catch block will run. If an exception does not get thrown, then the try block will finish and execution will continue after the catch block. Also, the print stack trace method is often very helpful in tracking down or finding errors. So this is the rest of the code that's not shown. Private void run tests. We have list.addFirst2, so I'm inserting the integer 2 into the linked list, and then I'm calling systemoutPrintln list.removeLast. So I'm inserting in first position and removing from last position. So below here we have the addFirst method. Node new node equals new node, and then the object parameter. New node.next gets head, head gets new node. All right, I want to take a look at these with the sketchpad and insert a node. Let's look at what happens here. So again, I'm going to go back and reload my slide that has my initial linked list. Okay, so I'm going to add first. So I'm going to make a new node, and we will call this new node X. So our code said new node.next gets head. New node.next gets head. Head gets new node. Head gets new node. Is this linked list correct? It appears to be. The head is X, so we go from X to A to B to C to D. This list appears to be in a consistent state. It appears to function just fine. It appears to be correct and consistent. New node.next gets head, head gets new node. Looks fine. So we run our code, and this is the result. Here's our remove last method. We insert first and remove last. eTemp equals tail.data. So we have a new variable eTemp, and it gets tail.data. This piece here, whatever it is, this works correct. We see no problems. This looks like code that should work perfectly, yet it does not. So when we run our driver program, we see the following results. We have a null pointer exception. We used to try catch block, and so we now know that the error occurred on line 91 in our linked list in the remove last method. When you look at these stack traces, look at the first line, not the last line. Very often students will go to the very end of a stack trace, and that's the main method linked list checker.java line 24, but the error is not there. Because the top of the stack contains the code that was running when the error happened, that's where you need to look. So go to the top of the stack trace, not the bottom. So I've put this in bold. We have remove last linked list ds.java line 91. So looking at 91, we have eTemp equals tail.data. So what causes the null pointer exception, the crash, is the use of the dereference operator, the dot operator on something that's null. Null.data. If tail.data does not exist, then you're going to get a null pointer exception. So this appears to be correct code, yet it has failed. Why? What is the problem here that has caused this to fail? So again, let's return to our sketchpad and take a look. I'm going to clear this. Imagine that we have the empty state. This is the head pointer, and this is the tail pointer. So both of these are initialized to null when the list is created. Now we insert a new node in first position. Let's call it A. We inserted a 2. This is null. So our code was new node dot next gets head. Okay, that does work. New node, the A, dot next gets head. Well, head's null. So we overwrite this null with this null. It's still null, so that's no change. And then the last line of code we have is head gets new node. Okay, that is also correct. So what we've done actually is correct here. The problem is what's missing. What's missing is the case where if the list is empty, you have to check to see whether or not the tail pointer should have been updated. This is an error. So now we say tail.data, and we're hoping to get the 2 out, but we don't. We get null.data, tail.data, and this causes a null pointer exception. Therefore, our code that we use to do this insertion is wrong, even though the error actually happened in the removal. So this is what you have to watch out for. There is a case here we missed. So the code we had was correct. We made a new node, and then we said new node dot next gets head. That is our new node here. The next field gets the head. So if we do another insertion now, let's say we have a B, and we're going to insert it now. This is the new node B. New node dot next gets head, the A. And then we have head equals new node. And this also works. So the code is not incorrect. We go from B to A. This is correct. The problem is we forgot to update the tail pointer, which led to a null pointer exception when we tried to access the data at the tail. So first we have to have a test here. If the head is null, if the list is empty, then head equals tail equals new node. I cannot write, my apologies. Head equals tail equals new node. Else all right, so with our revised code, let's see what happens. We start with the empty state. So head is null, tail is null. The list is empty. Now we're going to do an insertion first, in first position. Here's our new node, and we have the next initialized to null. If head is null, it is, then head equals tail equals new node. So this is just chaining. We could have said head equals new node, tail equals new node. But head equals tail equals new node accomplishes the same thing, and it's a little bit shorter. Now we have our list in a consistent state. Now let's add another node and see if the code is correct. So I'm going to add another node, and I'm going to put it here because we're inserting first. B. This is our new node. All right. If head equals null, it's not. New node dot next. New node dot next gets head. Head is A. New node dot next gets A. And then head gets new node. The new node is B. Head gets the new node B. So we go from B to A, and this is the end of the list. We are now in a consistent state. In other words, the problem was caused because we were missing a statement in our insertion code, a test to see whether or not the list was empty because it's a different case. The behavior in that case needs to be different. So I want to take a look at some different operations here. The first one I want to look at is a traversal. So what we want to do here is see whether or not the linked list contains, or whether or not the element is in the list. So this is a basic traversal operation. Again, I'm going to start with a linked list. All right, so let's put data in here. 17, 6, 5, 9. All right, I want to write code to see whether or not there's a 5 in this list. Is there a 5 in the list? So I must start at the head to traverse the list. I cannot traverse the list from the tail. That's really only useful for insertion. I will need to be able to traverse this list, so I will have to change references or change pointers, but I don't want to change anything that's in my list now. So I can do this by using a temporary pointer or a reference. So our code for contains looks something like this. Node E temp equals head. So now I have another variable called temp, and it's assigned the value of the head. So we now have two pointers that point to the first node in the list. The head points to the first node in the list, and temp points to the first node in the list. Now I can change temp at will, but that will not have any effect on the linked list. So these variables here, the head, the tail, and the nodes inside, we're not going to modify them. While temp is not equal to null. So I'm going to run this temp off the list. I'm going to start with temp pointing to the head, and then I'm going to go to node number 2, number 3, number 4. I'm going to go until I find this null link, and that terminates the end of the list. Now there are two possibilities. Either the 5 is in the list or it's not in the list. And so we need to handle both cases. What we don't want to do is run off the end of the list and attempt to access node that contains, or rather a null node with a dot operator. That will cause us to crash. So while temp is not null. Now we must use the comparable interface to compare the elements. If comparable E obj dot compare to temp dot data equals 0, return true. If you find it, then just return true. So this will stop the method right here. Otherwise, temp gets temp dot next. Now if we fall out of this while loop without having returned to true, then it's not in the list. We return false. All right, I want to talk about this comparable line here. If comparable E object. So we must cast this object, and this is what is passed in as the parameter. This is what we're looking for, the parameter. if it matches temp.data, so we're looking at the 17, then the 6, then the 5, then the 9, we're looking for the 5, so once we find it, we should return. So this code is very much like writing if obj is equal to temp.data. This is the use of the comparable interface. So I'm going to trace through this and see what happens. So our initialization is done here. We have node temp equals head, and it does. Head is A. While temp is not null, it's A. If comparable obj dot compare to temp dot data, this is the obj. If 5 is equal to 17, it isn't. So we don't return true. We have temp gets temp dot next. Well, temp is A dot next is B. Therefore, temp gets B. We've just moved down one. Again, we're at the top of the while loop while temp is not null. Well, it's not null, it's B. If 5 is equal to 6, B dot data. It's not, so we don't return true. We fall down to the next line. Temp gets temp dot next, and temp becomes C. So we're at the top of the loop again. While temp is not null, and it's not, it's C. If 5 is equal to 5, it is. We return true, and it contains that element in the list. So we return true, and we're out of the method. What I want to call your attention to is how we move down the list. Temp gets temp dot next. So temp started out as A, then it got B, then it gets C. If we were looking for something not in the list, then it would have gotten D, and then it would run off the list. So let's look at this scenario. Let's assume that instead of a 5, we're looking for a 7. So when we started out, our variable temp has A. It points to the first node in the list. We compare the 17 and the 7. They're not the same. We don't return true. Temp gets temp dot next. So we get B, then C, then D. So let's move down to where temp equals D. While temp's not null, it isn't. Is 9 equal to 7? No, it's not. We don't return true. We say temp gets temp dot next. Temp D gets temp dot next. Well, temp dot next here is null. So now temp gets null. Temp is null. We come around with the while loop here. While temp is not null, but it is null. So we fall out of the while loop and we return false. There is no 7 in the list. The next one I want to look at is insertion. So we examined the add first already. Recall that this code is defective because it's missing a case. What we were missing was the case that the list is initially empty. Then we need to set both the head and the tail to the new node. So what are our cases if the list is empty, if the list is not empty? Are there any cases we haven't considered? The thing we want to ask yourself is there any operation, is there anything or any case that can occur that would cause any of the class level variables to change, i.e. the head or the tail? Now we haven't really talked about or considered current size here, but it's important to keep track of the size of the list, and so you want to make sure that when you insert, you do current size plus plus. When you remove, you do current size minus minus. Okay, so we're looking at insertion here. We considered our cases. So for an unordered list, we may want to add to the first position of the list or add to the last position of the list, either one. But for an ordered list, we want to put them in correct order. That is, we need to insert them in the right place. So inserting first or inserting last makes no sense for an ordered list. So I'm going to do an ordered insertion example. So we need to consider several cases. The first case is, what if the list is empty? What if the list is not empty? What if insertion happens at the head or the tail or somewhere in the middle? Now I should add that for an ordered linked list, we're not going to have a tail pointer. So perhaps I should have put if insertion happens at the end. But you want to look at the cases, and you may or may not need to do something with each of those cases, but you do want to identify them first. So let's switch to the sketch pad here. So when we're going to do an insertion here, we need to find where it goes. Now it's possible that the list might initially be empty, and we may want to check for that. So here's our insertion. Let's put some values in here so we have something to look at. 2, 4, 5, and 9. So our list is now in order. Let's assume that we're going to insert the value 8. So the first thing we do is we create a new node. I'm not going to write the code for that. We put node E, new node equals new node. And now we have to find where it goes. We're going to do this by creating additional pointers or references that we can use. I want a previous and I want a current. Now the idea here is that we want to have this or configure this such that current is going to point to D and previous is going to point to C. In other words, our new node will be inserted in between previous and current. And if we're consistent about how we approach this, it will greatly simplify doing our insertions. So we're going to take this approach. Now it's possible that the node we're inserting might be, say, with the data value of 1. So it's possible it might be in first position. So we're going to initialize our list variables here, our temporary variables, such that we're consistent. If it goes in first position, it goes before the head, then it would go again in between these two. It would go before current. So this is our initial setup. We have the previous before the beginning of the list and current pointing to the first element in the list. So what we want to do now is to write a loop, and we're going to loop until current passes the insertion point. That is, we want to loop until we get 1 past where it goes. So as we examine this situation, looking at A, we're inserting an 8. This gives us no real information. The 2 is less than an 8. So we don't have a stopping point. We keep going. The 4 is less than an 8. No stopping point. The 5 is less than an 8. Again, we haven't reached a stopping point. But the 9 is not less than an 8. It's larger than the 8. So this tells us we have to stop. The new node must go before the 9. Therefore, it goes in between previous and current. So, while current is not equal to null. So we have this test first and comparable. Again, a cast to comparable. E. Comparable. E. The object we're inserting. Dot compare to. current.data. Is greater than or equal to 0. So while the object we're going to insert is greater than or equal to what we're looking at now, keep going. 8 is greater than a 2, keep going. 8 is greater than a 4, keep going. 8 is greater than a 5, keep going. 8 is not greater than a 9, stop. So when we fall out of the loop, current will point to D, that's our stopping condition, and previous is going to point to C, the 5. All right, I need to make a comment about current not equal to null here. It's possible that the node we're inserting goes at the end. Now this simple example, or this template I have, has a tail pointer. So I'm going to go ahead and get rid of this now because we would not have a tail pointer with an ordered list. It makes no sense to have it, and the overhead involved in keeping that up to date makes it not worthwhile. So we typically have a tail pointer only with an unordered list. All right, so it's possible that we might run off the end. Suppose we were inserting a 10, then is 9, or I'm sorry, if we're inserting a 10, then we have the object 10 is greater than 2, yes it is. It's greater than a 4, yes. 10 greater than 5, yes. 10 greater than 9, yes. And then we move down again and current becomes null. That's where we want to fall out of the loop. We don't want to keep going. So we will never have a problem with a null pointer exception caused here, because if current were equal to null, we would fall out of the loop and we would not perform this test, which would cause a null pointer exception. So it's important that you do this first. This is called short circuit or lazy evaluation. That is, with Booleans of this type, you have A and B. If A is false, then there's no reason to look at or test B, so it doesn't even get tested. That's why it's called lazy or short circuit evaluation, because this is true if and only if A is true and B is true. So if A is false, then the entire statement is immediately false. So this protects to make sure that we won't get a null pointer exception from testing null.data here. All right. So in our loop, we keep going. So we have previous equals current. And we have current equals current dot next. And this is the end of our while loop. All right. So we've got our initial values set here for previous and current. And I want to look at what happens with the insertion of an 8. So we enter the while loop, and while current is not null, it's not, it's A. We do a test. Is 8 equal to 2? Or greater than or equal to 2? Yes, it's greater than a 2, so we keep going. We say previous gets current. So previous gets A. Current gets current dot next. Current gets B. Again, we loop around while current's not null. Well, it's not, it's B. And 8 is greater than or equal to the 4. Well, yes, that's true. So previous gets current. Current gets current dot next. We loop back around. While current's not null, it's not null, it's C. While 8 is greater than 5, it is. We keep going. So we have previous gets current. This gets C. Current gets current dot next. It gets D. We loop back around. Well, current's not null. It isn't null, it's D. And 8 is greater than or equal to 9. 8 greater than or equal to 9. This is the object here, OBJ. Current.data, 9.data is this. Therefore, the statement is false. 8 is not greater than or equal to 9. We fall out of the loop. So we fall out of the loop, and now previous points to C and current points to D. So now we have found our insertion point. All right, I want to erase and make room, and we want to look at our cases now. We've found the place where it goes. We know where it goes, and now we need to insert it into the list. Now there's certain possibilities we need to bear in mind. The first is it could go in first position. It could precede the A node. If it does not precede the A node, it could be in last position and follow D, or it could be somewhere in the middle. So we have these different cases to consider. So let's consider these one at a time. What if it's in first position? Well, if it's in first position, that is, we're inserting, say, a 1, then current would be A and previous would be null. So we can tell that we have to insert in first position. So if previous is null, you could also say if current is equal to head. There are different ways it could be done. But if previous is null, then it goes in first position. So new node dot next gets head. And then head gets new node. So this is just an insert into first position, and we have seen this before. Now, will this work if the list is empty? If the list is empty and previous is null and current is null, then we have new node dot next gets head. All right, new node dot next gets null. It would already have been null. That works. Head gets new node. Yes. So this works whether the list is empty or not empty. It works in both cases. All right, what if it goes in last position? Else, if current is equal to null. This will happen if we ran off the end of the list. So if we were inserting a 10, then current would be null. So in this case, what do we want to do? If current is null, then previous dot next gets the new node. So in this case, if we have an E and we're inserting off the end, so this is a larger value, say 20, what we need to do is simply update this one pointer to E, and it's inserted. So if current is null, we've run off the end, then previous would point at the last node in the list, the D. So previous.next gets new node in this case, and it's hooked in. Otherwise, it's in the middle somewhere. Else, previous.next gets new node, and then new node.next gets current. So let's examine this now for the base case, the most common example. It goes somewhere in the middle, so we'll look at the 8. So we will create a new node here. Let's call this X. And it's got the data value of 8. So at this point, C is previous and current is D. Previous dot next gets new node. Previous C dot next gets new node. Previous dot next gets new node, that's the X. Now new node dot next gets current. New node, the X, dot next gets current. Okay, so now we go from A to B to C to X to D. So now we have inserted this in between C and D. A deletion example. So again, the case is to consider. If the list is empty, you don't want to crash with the null pointer exception. If the object parameter you're searching for is not in the list, then you can't remove it. If it is in the list, but it's at the head, what if it's at the tail? What if it's somewhere in the middle? What if removal of the element will cause the list to become empty? If it's an unordered list and you're removing some arbitrary element, then the possibility exists that you might have to update the tail pointer. And if this is the case, then you cannot neglect or forget to do that. So I want to look at an example here of a removal. Again, retrieving my linked list. So let's give the list some elements here, 2, 4, 6, 8. And since we're doing ordered, we're going to get rid of the tail pointer. So to delete this node, we have to find it first. We've looked already at an algorithm for traversing. We simply use a while loop to move down the list. But there's an issue here. Let us say, for example, we want to remove the 6. In order to remove the 6, what we have to do is change this linked list. We want to change this pointer, the preceding one. This needs to become D. So this has the effect of going from A to B to D. So we actually jump over this node. And since there are no references anymore to the node C, then it's garbage collected and gone. So this is how we delete a node. So to make this happen then, we absolutely must have a trailing pointer. We must have a reference to the preceding node, or the node before the one we want to delete. So we can use the same idea now of a previous and current to find the node to delete and have a trailing node that points to, or a trailing pointer rather, that points to the node before it. We can use that to do the update. Then we need to bear in mind the possibility that we may have to change the head or change the tail pointer if there is one in this case. So starting with our basic template here, we want to delete a node from this list. So we must find it first, but we need a trailing pointer so that we can remove it. So again, I'm going to have a previous and a current. Now it's possible that the list might be empty. If the list is empty, then current would be set to null. So this matters because it's one of the cases. So we'll revisit this in a moment. So now let's look at the while loop. While current is not null. Again, this protects us from running off the end of the list and trying to dereference something that's null and thus crashing with the null pointer exception. And comparable E. OBJ, this is the object we're trying to find and delete. Dot compare to current dot data. Is not equal to 0. So we're going to go until we find it. So when current dot data is equal to the object, then we fall out of the loop. Current will point to the node to delete, and previous will point to the node before it. So while this is the case, previous equals current, current equals current dot next. All right, let's make the assumption again that we're going to delete a 6. We will delete the 6. So this is our object OBJ. All right, we start our while loop. While current's not null, it's not, it's A. And 6 is not equal to 2. Well, that's true. The 6, OBJ, is not equal to current.data, the 2. So previous equals current. Current gets current.next. So we are just systematically moving down the list. Looping back around while current's not null. It isn't, it's B. And 6 is not equal to 4. That's true, we keep going. So previous gets current, the B. And current gets current dot next, which is C. All right, we loop back around while current's not null, and it isn't null. While 6 is not equal to 6. Object equal to current dot data. Well, this isn't true. We fall out of the loop. So we fall out of the loop here, and now we have previous is B, current is C. So the node to delete is C, and the node before it, the B, has the reference we need to update in order to cause the 6 to be removed from the list. So again, to make some space here, I want to erase and look at the cases. All right, the first case I want to consider is current is null. That is, it's not found. This is the not found condition. All right, this will happen if current is null because we will have run off the list. So here previous would be D and current will be null. That means that it's not in the list. So if current is equal to null, it's not found. So depending on what return value you have, if we have a Boolean, then put return false, not found. We don't need an else after return statement. But there's another possibility. What if it's in first position and the head pointer would have to be updated? In that case, we can tell if it's in first position if previous is null. If previous is equal to null. Or again, we could have said if current is equal to head. Then in this case, head gets head dot next. So in this case, suppose we were deleting the head, then head gets head dot next would change this to a B, and so A would be garbage collected, and the first node in the list would be the B. Notice, though, that we have more information based on this. If this doesn't happen, if previous is not null, what does that tell us? There's a very important issue here. If previous is not null and current's not null, then there are at least two elements in the list. And that becomes essential for the next part. Else previous dot next gets current dot next. Now we couldn't do this unless we were certain that previous is valid, it's not null, and current's not null, which means there are at least two elements in the list. If there were only one element in the list, then one of these, either the previous dot next or the current dot next, would cause a null pointer exception to occur, dereferencing a null reference. Since they're neither one null, we know this, current's not null and previous is not null, then we say previous dot next gets current dot next. Okay, so with the example we have here, previous dot next gets current dot next to D. So this in effect jumps over this node, and it is garbage collected and removed from the list. And then we will simply have at the bottom here, return true as the last statement. Now the other case I ask about, what if the list were empty? What if we had this scenario? Well, what happens with our code? If current is equal to null, return false. All right, well, we initialize current to the head. Therefore, this code works for the empty case as well with no further changes. So this concludes our lecture. This is a lecture about manipulating and working with linked lists and avoiding null pointer exceptions and inconsistent states. And we will continue this discussion with the next lecture where we take another look at some of the common methods with linked lists.